Okay, we're going to take a look now at how we can find a power series from a power series we already know. So we have some series that we've found. We've found the series for sine of x, cosine of x, e to the power of x, 1 over 1 minus x. Using these series that we already know, we can manipulate them to find the series for more functions. So here's some that we already know, 1 over 1 minus x. We found this by the geometric series, so we're multiplying by x, which would be our common ratio. Our initial term is 1, so this adds up to a over 1 minus r. The initial term a is 1, common ratio r is x, so this is 1 over 1 minus x. So the function 1 over 1 minus x is equal to the sum of x to the n. We derived sine of x using the formula for Maclaurin series. We derived cosine of x the same way. And e to the x we derived the same way. So here are 4 series that we already know. Now, we have some ways we can come up with a power series for a function. We can derive them using the Taylor series. And this is usually a pretty nice way to go about doing it, but an issue we run into is if you have some function where the derivative, or the second derivative, or the third derivative starts to get very complicated, then this starts to be rather difficult to do. So we've also seen that we can take a power series that we already know. We can take the derivative or the antiderivative to construct a new series for a new function. And we'll see today that we can also find a series for a new function using addition, subtraction, multiplication, division, or substitution with a Taylor series that we already know. So we're going to find the Maclaurin series for 1 over 1 plus x. Notice this looks a lot like one we already know, 1 over 1 minus x. Well, all we have to do is a substitution, replace x with negative x, which will give us 1 over 1 minus negative x, or 1 over 1 plus x. Replace x with negative x in the power series, and simplify that to be negative 1 to the n times x to the n. And just through that substitution, we now have a series that represents this new function, 1 over 1 plus x. Now we're going to find a Maclaurin series for 1 over 1 plus x squared, and we're then going to take the antiderivative to find the series for inverse tangent of x, because the antiderivative of 1 over 1 plus x squared is inverse tangent. So first let's find the series for 1 over 1 plus x squared, again by using a substitution. Since we now know that 1 over 1 plus x is negative 1 to the n times x to the n, we can replace x with x squared. That gives us the function 1 over 1 plus x squared, and that's equal to the sum of negative 1 to the n times x to the 2n. And notice the interval of convergence here is from negative 1 to 1. We could confirm that by using the ratio test. Now, if we take this series and integrate, take the antiderivative of 1 over 1 plus x squared is inverse tangent. On the right side, we increase the exponent by 1 and multiply by the reciprocal of the new exponent. We have our constant of integration, but it turns out if we just let x equal 0, we can see that that constant is 0. And so we end up with inverse tangent of x is the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, interval of convergence from negative 1 to 1, including both endpoints, and we could confirm that by checking those endpoints individually. Notice this series looks a lot like sine, the difference being that on the bottom it's 2n plus 1 rather than 2n plus 1 factorial, so make sure that you notice that subtle difference there. Now we're going to find the Maclaurin series for x squared times cosine of x. So we start with the series that we know, cosine of x. We multiply it by x squared. Well, that just means we multiply each term in the series by x squared, which simplifies to x to the 2n plus 2 over 2n factorial, all of that multiplied by negative 1 to the n. All right, we're going to find the first 4 non-zero terms for the Maclaurin series of e to the x times the inverse tangent of x. So we want to make sure we have each of those series, the first few terms. We're going to multiply these together. Well, when we multiply polynomials, we know that we multiply every term in one polynomial times every term in the other. Now, with infinite polynomials, with these series, that's impossible to do. But we only need the first 4 terms, so we just have to go through and multiply enough of these terms together to come up with those first 4. So we take the x from inverse tangent times the 1 from e to the x, and that gives us x. X times x is x squared, x times x squared over 2 factorial, x cubed over 2 factorial, and so on. Once we've got out to x to the 4th over 3 factorial, that's 4 terms, so we don't need to go any further with multiplying by x. Then we move to the next term in that second polynomial there, the negative x cubed over 3. Multiply that by 1, you get negative x cubed over 3. Multiply by x, you get negative x to the 4th over 3. We've gone out to degree 4, that's far enough. And then we have x to the 5th times 1, that's already out to degree 5, that's far enough. And if we were to multiply any more terms in this, they would be beyond the 4th term, so we don't need them. Now we collect like terms, and we have the first 4 terms for this series. One nice application of a power series is it allows us to approximate an integral when we might not be able to evaluate it otherwise. So we're going to use the first 4 terms of the series for e to the negative x squared to approximate the integral from 0 to 1 of e to the negative x squared. Because this is a function that we cannot find the antiderivative for, so we approximate it by turning this into a series. Well, we know the series for e to the power of x. We can use substitution to find e to the negative x squared, so replace all of your x's with negative x squared and simplify. And now take the integral from 0 to 1. Now on the left side, we don't know how to evaluate that, so we take the antiderivative on the right side, evaluate from 0 to 1, which gives us these terms here. Now notice the question asks for the first 4 terms. I've gone out to the first 5, so for the first 4 terms we can just stop after minus 1 over 42. So this integral is approximately 1 minus a third plus a tenth minus 1/42, which ends up being 0.743. So to think of that in terms of a graph, the integral from 0 to 1 of e to the negative x squared, that graph has an area from 0 to 1 of 0.743 approximately. Well, we want to know how accurate that is, and the alternating series estimation theorem tells us that the error is less than the first unused term. Since this series alternates, we can just find that first unused term, which is that 1/216th, which is approximately 0.004. So we know that we are off by no more than about 4 1,000ths.